Lighthouse Scientific Education presents a lecture in the Stoichiometry series. The topic, Stoichiometry, Advanced Concepts. Material in this lecture relies on an understanding of the previous lectures, balancing chemical equations, stoichiometry, problem solving, and since this lecture contains gases, gas law, one condition. Much of this lecture is an extension of the previous lectures on stoichiometry, and a brief review is offered, including a list of the types of stoichiometry problems and the steps for solving stoichiometry problems. Then it is on to the first of the two main topics of this lecture, limiting reactants or limiting reagents. This topic is probably the one of most interest in the lecture. The second topic is gas stoichiometry. It is divided into problems that use molar volume and problems that use the ideal gas law. In the stoichiometry problem-solving lecture, a list of types of stoichiometry problems is given that is based on the units of the current and desired substance in the problem. There are four general types. There are the mole-to-mole problems. These types are addressed in the mole ratio lecture. There are also mass-to-mass and mass-to-volume or volume-to-mass problems, and they are covered in the stoichiometry problem-solving lecture. The volume covered there was volume of solution and required a concentration. Not discussed in those lectures is the fourth type, volume to volume. While these volumes can be solution volumes, they can also be volumes of gas. An example of this type of problem includes finding the liters of gas, CO2, produced in a combustion reaction that starts with 25 liters of the gas, oxygen, and finding the volume of hydrogen gas at STP that is produced when 4.25 grams of aluminum is completely consumed in a reaction with an acid. Both of these types of problems will be addressed later in the gas stoichiometry part of the lecture. Also in the stoichiometry problem-solving lecture are 5-step procedures presented for the development of a solution to a stoichiometry problem. These steps work just as well for the topics of this lecture. As a review, Step 1, write out and balance the chemical equation of the reaction in the problem. Step 2 uses the basic problem-solving technique of searching the problem for known and unknowns. Identify the given or current substance and the wanted or desired substance. Also note amount with the current substance. When a compound in the problem is a gas, factors like pressure, volume, and temperature are also of interest. In this step, the student also needs to verify that there is sufficient material for the reaction to proceed to completion. Reactants that are not part of the stoichiometry problem often have terms like enough or abundant to signify that they are not limiting reactants. More on that topic momentarily. Step 3 is to write out the mole ratio, coefficients and substances from the balanced chemical equation, and to put this ratio in the center of the solution equation. The mole ratio is the heart of the overall solution and allows information about one substance to be converted into information about another substance. Orientation of the mole ratio has the desired substance with its mole amount from the balanced equation over the current substance with its mole amount from the balanced equation. Step 4 is the get into moles part of the stoichiometric solution. Convert given or current units, be they grams or mils or whatever, into moles of the given or current substance. For the most part, this step uses previously developed skills that should be relatively manageable to the chemistry student at this point of their studies. The conversion factor is placed in front of the mole ratio in the solution equation. Canceling units and doing math up to this point will give us moles of the desired substance. These moles will need to be converted into the unit type asked for in the problem. Often those units are in mass or molarity, but in this lecture, they will also be the volume of a gas. Place this conversion after the mole ratio in the solution equation. The moles of the wanted or desired substance should cancel out. If not, there might be an orientation problem with the conversion factor in this step. The first 3 steps are the mole ratio steps. Step 4 is getting into moles, and step 5 is getting out of moles. Most students will have some exposure to the first of the 2 major topics in the lecture. It is limiting reactants or limiting reagents. Consider a chemical reaction involving 2 or more reactants. We'll just show 2 here. In the real world, one reactant is almost always used up before the other or others. It is impossible or almost impossible to match up exact amounts of reactants. When one reactant is used up, the reaction will stop. There should be some remaining amount of the other reactant. Not surprisingly, having less of one reactant limits the amount of product formed. The reactant that is used up is called the limiting reactant or reagent. Some textbooks call it a limiting reactant and some call it a limiting reagent. They are, in essence, the same thing and can be used interchangeably. The other reactant or reactants are said to be in excess. They are called the excess reactants or reagents. Before proceeding with solving limiting reagent problems, let's make sure we fully understand the concept. To do so, we will invoke a simple cartoon. Say that there's an automobile factory, and it currently has 4 car bodies. The factory makes complete automobiles, so these bodies still need additional parts. In chemistry terms, they need other reactants to produce automobiles. Say that the automobile factory has 6 sets of 4 tires. It has 24 tires that it can use with its 4 car bodies. Question: how many complete cars can be made with these components? Can they make 6 cars, as the amount of tires would suggest? Or can they only make 4 cars, as the number of bodies would suggest? Right, it can only make 4 cars. There will be an excess of 8 tires. In our cartoon, the car bodies are the limiting reactant or reagent. The sets of tires are the excess reactant or reagent. To balance this equation, we would have to add the additional 8 tires on the product side. Now, with that same logic, consider a chemical reaction that begins with 10 sodium atoms. The sodiums are combined with 4 Cl2 molecules. There are 8 chlorine atoms in the 4 Cl2 molecules. Sodium and chloride readily react with each other. In this cartoon, with these quantities, 8 sodium chlorides are produced. There are 2 sodium atoms that did not or do not have chloride atoms to interact with. They are in excess. The chlorine is the limiting reagent or reactant, and the sodium is the excess reagent or reactant. To keep the 2 sides numerically balanced, we would add the 2 sodium atoms to the product side. The concept of a limiting reactant seems straightforward enough. But when and where does it come up? Limiting reactant problems often give amount values for 2 or more reactants and ask for an amount of product. The problem has an expectation that one reactant is the limiting reagent. It is not as easy as choosing the one with the smaller number. Unfortunately, the only way to determine which is the limited reagent is to compare how much product each reactant would produce, giving its starting amount. Actually, there are other ways of doing this, but we're going to focus on this one method. To determine which of the reactants is a limited reactant and the amount of product it can form, for each reactant, use stoichiometry to get the theoretical amount of a single product. If there are multiple products, just pick one. It doesn't matter which one. To be clear, each reactant with a given amount has its own set of calculations. This is a multiple stoichiometry solution problem. Once that is done, choose the reactant that produces the smallest amount of product. The limiting reactant will not produce as much product. Returning to the cartoon description of the sodium chloride reaction, we can see how this logic of addressing limited reactant problems plays out. The problem wants to know whether the sodium or the chlorine is the limiting reactant. It will have to give values for both the sodium and the chlorine. In this example, we look directly at atoms and molecules, but with any real limited reactant problem, the amount values will be in moles. The basic question is to ask how many sodium chlorides can be produced from 10 sodium atoms. That is assuming that there is an abundance of chlorine molecules. The answer to that is, of course, 10 sodium chlorides. 1 sodium for each sodium chloride. The problem is easy enough to do by inspection, but if the value of sodium was given in grams, then we would have to find the amount of sodium chloride using stoichiometry. The same question could be asked with a chlorine. How many sodium chlorides can be made if there are 4 chlorine molecules or 8 chlorine atoms? The answer is 8 sodium chlorides. If the value of chlorine was given in grams, then we would have to find the amount of sodium chloride using stoichiometry. A direct comparison of the amount of sodium chlorides produced has the 8 sodium chlorides from the chlorine being less than the 10 sodium chlorides from the sodium. Cl2 is the limiting reactant, and sodium is the reagent or reactant in excess. Bringing back the steps in solving the stoichiometry problem, a couple minor modifications are made specifically for getting limited reactants. The first is to treat all reactants that are given specific values as given substances in their own equation. Each reactant is going to have its own stoichiometry equation. In the previous example, the sodium would have its own equation and solution, and so would the chlorine. As for the desired substance, pick any single product. Be sure to pick the same product for each reactant so that the amount values can be compared directly. Determine the mole ratio for each reactant and the product. Different reactants with their own stoichiometry equations will need their own mole ratios. The nice thing about finding a limiting reactant is that a direct comparison of product amount can be made after the moles of the product have been calculated in the first 4 steps. Getting out of moles is not necessary for determining limited reactants. It is just as valid to compare moles of product determined for each reactant as it would be to compare, say, grams. Select a reactant that gives the smallest number of moles of product. That will be the limited reactant. If the problem wants the product amount from the limiting reactant to be given in grams or mils or molarity, add back in that get out of mole step. Do not fall into the trap of getting a product value in grams or mils from the excess reactant, because that is more product than can be made with these starting amounts of reactants. A couple practice problems are provided to help solidify the process of finding a limiting reactant. Which reactant is the limiting reagent when 10 grams of O2 react with 2.5 grams of H2? How many grams of H2O can be produced? This is a limiting reactant problem because it gives amount values for 2 reactants and asks for an amount of product. Solving the problem is really solving 2 stoichiometry problems, and they both begin by balancing the chemical equation. This rather simple tally shows the reaction to be balanced. Step 2 has us finding the known and unknowns. The modification to the stoichiometry steps says to treat all reactants with given values as given substances in their own equation. The reactant oxygen is given a specific amount. That is added to the setup as a known. The reactant hydrogen is given a specific amount and is added to the setup as a known. As for the unknown or the desired substance, any single product will do. Well, all we have is water, and it specifically asks for that, so it is our unknown. include the wanted or desired units in grams. Step 3 is to get the mole ratio from the balanced chemical equation. The modification to this step says that each given substance will need its own mole ratio. Both reactants will use the product of water as the desired substance in their mole ratio. So the numerator of both mole ratios will be 2 moles of water. For the reactant oxygen, the denominator of the mole ratio will be 1 mole of oxygen. The first mole ratio is done. The other reactant is hydrogen. Its 2 moles will be in the denominator of its mole fraction. If getting 2 knowns and 2 mole ratios at the same time just seems confusing, then do these stoichiometry problems one at a time. Calculate moles of water from the starting amount of oxygen, and then start over and calculate the moles of water from the starting amount of hydrogen. Here we're going to do them side by side, but that is really just to show the similarity of the process. Our objective is to compare moles of product determined for each reactant. Remember, we're looking for the smaller product value. This is where the stoichiometry solution equation will come in. Starting with the given value of oxygen and its mole ratio. That mole ratio is placed in the center of its solution equation. Be sure moles of oxygen are in the denominator. Step 4 is getting the 10 grams of oxygen into moles of oxygen. The conversion factor needed here is the molecular weight of oxygen, with grams of oxygen in the denominator, so that they cancel out with grams of oxygen in a given amount. Moles of oxygen also cancel out, leaving moles of water. Now, we can convert moles of water into grams of water with the molecular weight of water. But if our objective is to compare amounts of product produced for each reactant, then stopping at the moles of the desired substance is just fine. In other words, the 0.625 moles of water produced by the 10 grams of oxygen will serve our goal. We will now do the same exact thing with the starting amount of 2.5 grams of hydrogen and its mole ratio. That mole ratio anchors its own solution equation. Getting into moles of hydrogen from grams of hydrogen uses the molecular weight of H2. Again, grams of H2 have to be in the denominator so that they cancel out with the given grams of hydrogen. Moles of hydrogen cancel out, leaving moles of water. Doing the math specifically produces 1.24 moles of water. The limited reagent is the one that produces the smallest quantity of product. Even though there is 4 times as much oxygen as hydrogen, there is still insufficient amount of oxygen to completely react with all of the hydrogen. At this point, there is no longer a need for the excess reactant. To get the theoretical amount of water that could be produced in this reaction, only the limited reagent or reactant is used. Bringing in step 5, getting out of moles of water into grams of water uses the molecular weight of water. At most, 11.3 grams of water could be produced with these starting amounts. The second problem asks how many grams of ammonia could be produced in a reaction of 5.0 grams of nitrogen with 1.0 grams of hydrogen. This is a limited reactant problem because it gives values for 2 reactants and asks for amount of product. The expectation is that one of the reactants is limiting. Limiting reactant problems are essentially stoichiometry problems. That means balancing the chemical equation. There are 2 element types in this reaction with even numbers of atoms on the reactant and product sides. Step 2 in the process is to get the known and unknowns. In all limiting reactant problems, there will be more than one known quantity. There should only be one unknown. Given is 5.0 grams of nitrogen. Add that to the setup. Also given is the 1.0 grams of hydrogen, which is also added to the setup. To find which of these reactants is the limiting reactant, we must find how much each can produce of any single product. The question asks for amount in grams of the lone product, ammonia. That goes in the setup as the unknown. It is the desired substance. Step 3 is to find the mole ratio. For limiting reactant problems, that's finding a mole ratio for each reactant that has a specific given amount. Again, this process can be done in separate parts. One part would be determining the amount of moles of ammonia from the 5.0 grams of nitrogen, and when that is done, determining the amount of moles of ammonia from 1.0 grams of hydrogen gas. Both mole ratios will use the same desired substance. The 2 moles of ammonia will go in the numerator of both mole ratios. The mole ratio with the reactant nitrogen will be 2 moles of ammonia over 1 mole of nitrogen. For the second reactant, hydrogen, its mole ratio will be 2 moles of ammonia over 3 moles of hydrogen. These mole ratios will be used to calculate moles of ammonia that can be directly compared. The smallest amount of product will be coming from the limiting reactant. Starting with the reactant nitrogen and its mole ratio, which is placed in the center of its solution equation. The 5.0 grams of nitrogen needs to be converted into moles of nitrogen. In step 4, getting into moles. What converts grams of nitrogen into moles of nitrogen? The molecular weight. Be sure to put grams in the denominator so that grams cancel out, as well as moles of nitrogen. The objective is to compare amounts of ammonia produced by the 2 reactants. This can be done by comparing grams of ammonia or by comparing moles of ammonia. 5.0 grams of nitrogen can produce 0.357 moles of ammonia. The second reagent is hydrogen, and its mole ratio is placed in the center of its solution equation. The 1.0 grams of hydrogen are converted into moles of hydrogen through the molecular weight of hydrogen. Cancel grams of hydrogen and moles of hydrogen, leaving moles of ammonia. 1.0 grams of hydrogen can produce 0.330 moles of ammonia. We can directly compare the amount of ammonia produced for these 2 reactants. The 0.330 moles of ammonia is the smaller amount. The hydrogen is the limiting reactant. Nitrogen is in excess, and we no longer need to concern ourselves with it. Still not quite done with the problem, though. It asks for ammonia in grams, but what we now have is ammonia in moles. What conversion factor converts from moles of ammonia into grams of ammonia? That would be the molecular weight of ammonia, oriented so that moles cancel out, leaving units of grams. 1.0 grams of hydrogen can at most produce 5.6 grams of ammonia. Essentially, limiting reactant or reagent problems are comparing amounts from individual stoichiometry solution equations. There are plenty of places to make mistakes, so follow the procedure carefully. On to the second major topic of the lecture. Before proceeding with stoichiometry involving volumes of gases, a brief review of the parameters of a gas is in order. This material is covered in depth in the gas series of lecture. There are 4 parameters that define the behavior of a gas. They are the number of particles, that is amount and usually given in moles, temperature, which is a motion property, it is given in the Kelvin scale, volume of gas, which is of particular interest to this lecture, and pressure. P, which is the force exerted per area. These are interrelated properties. Alter one property, and one or more additional properties will change. Gas stoichiometry is no different than stoichiometry involving other states of matter. Problems are solved the same way. Get into moles, mole ratio, and then get out of moles. What differs with gas stoichiometry is that getting into moles is often from volume, and getting out of moles is often into volume. We will consider entry and exit from moles from two perspectives. The first is the viewpoint of the ideal gas law. It says that in any one condition, the four properties of an ideal gas are related as PV equals nRT. P, V, N, and T are the four basic properties. And R is the gas constant. It has units of all four properties and a numerical value dependent on the dimension of the unit types. The ideal gas law can be used to get into moles with a rearrangement of the ideal gas law equation. The variable for moles, N, can be isolated by itself on one side of the equation by dividing both sides of the equation by its neighbors, R and T. The R and T cancel out on the right-hand side of the equation, giving a modified ideal gas law that is solved for moles. Filling in values for P, V, R, and T will get into moles. Let's keep this arrangement of the ideal gas law with the get into moles part of the stoichiometry solution. As for getting out of moles, that same equation is employed, but this time it is solved for get out of moles into volume, V. Dividing both sides of the equation by volume's neighbor, P, pressure, and canceling out pressure on the left-hand side of the equation gives a modified ideal gas law equation for getting out of moles into volume. Let's keep this modified version of the ideal gas law equation with the get out of moles part of the solution. Many stoichiometry problems at this level of chemistry ask for a volume for the wanted substance. But the moles determined from the get into moles and mole ratio part can also be used with the ideal gas law to get out of moles and into pressure, or at a temperature, if enough information about the other properties is provided. There's only one way to use the ideal gas law equation to get into moles, but there are three ways to get out of moles when dealing with gases. In the stoichiometry problem-solving lecture, a graphical representation was used to visualize the 5 procedural steps and their orientation as a function of the 3 parts of the stoichiometry solution. That lecture focused on moving into and out of moles from mass, weight, and molarity of solution. Here it is gas. When getting into moles from volume, the ideal gas law equation is modified to isolate N, the number of moles. When getting out of moles, the ideal gas law can be modified to isolate pressure, temperature, or volume. We will limit our discussion in this lecture to just the volume parameter. A second consideration in gas stoichiometry problems is molar volume. We will limit our discussion to molar volume under standard temperature and pressure, STP. STP is an agreed upon set of common values. The standard temperature is 0 degrees Celsius, and that's an exact value. It corresponds to 273.15 Kelvin. The standard pressure is 1 atmosphere. That too is exact. 1 atmosphere corresponds to 760 millimeters of mercury or 760 torr. Important to our discussion is that at STP, 1 mole of gas occupies a volume of 22.4 liters. This is true for all gases. That moles of gas to volume ratio is referred to as a molar volume. It can be used as a conversion factor for getting into and out of moles. At STP, the relationship of 1 mole of gas to volume is 22.4 liters. A ratio or conversion factor can be written as 1 mole of the gas over 22.4 liters, or 22.4 liters over 1 mole. Both of these are molar volumes that are only valid at STP. Both of these are molar volumes that are conversion factors. Returning to the 3 parts of the stoichiometry solution, the STP molar volume, written as 1 mole over 22.4 liters, converts volume of the gas in liters into moles of that gas. That is getting into moles. Getting out of moles and into volume uses the reciprocal ratio, with liters in the numerator and moles in the denominator. That ratio belongs with this part of the solution. Returning to the graphical representation, we can add volume of the current substance at STP, being converted into moles of the current substance, with the molar volume written with liters in the denominator. Additionally, getting out of moles at STP uses the molar volume with moles in the denominator so that they cancel out with moles in the mole ratio. The key, of course, is to cancel units as a way of demonstrating the correct orientation of a conversion factor in the stoichiometry solution. Keeping this graphical representation in mind, it's time to solve a few stoichiometry problems involving gases. We will do 2 problems using molar volume and 2 problems using the ideal gas law. Starting with molar volume. Problem 1. How many grams of potassium chlorate, KClO3, are needed to decompose into 11 liters of oxygen gas at STP? We will assume that all the potassium chlorate decomposes as shown in this reaction. Is this a stoichiometry problem? Does it give information about one substance and ask for information about another substance? Yes, it does. Of the 4 types of stoichiometry problems listed earlier, this problem falls under the mass to volume or volume to mass type. And to be clear, the volume is volume of gas, not volume of a liquid solution. The first step in solving a stoichiometry problem is to balance the chemical equation. Is this equation balanced? A quick check shows there to be 3 oxygens on the reactant side, but only 2 on the product side, so no, it is not balanced. An absence of coefficients is also a good indicator that the reaction is not balanced. Since the objective of this lecture is not to practice balancing equations, the coefficients are added. Still, a double check is in order. There are 3 types of elements in this reaction, and a tally of atoms on the reactant and product sides shows there to be equal number of atoms. Step 1 is complete. Step 2 is to look for the known and unknowns in the problem, beginning with the known. The problem says that there are 11 liters of oxygen. Liters are the given unit. Oxygen is the current substance. The problem also asks for grams of potassium chlorate. It is the unknown. Grams are the wanted units, and potassium chlorate the desired substance. These are the known and unknown. Is the STP an important factor? Should it be included with the known and unknowns? Yes, it should. When dealing with gases, temperature and pressure are important factors that need to be included in the setup. Step 3 is to use the balanced chemical equation to find the mole ratio. The mole ratio will have moles of the desired substance in the numerator and moles of the current substance in the denominator. It is important to remember that values from the problem never find their way in the mole ratio. The balanced chemical equation for the reaction is independent of values given in the problem, and therefore, so is the mole ratio. From the balanced chemical equation, we see that there are 2 moles of the desired substance, potassium chlorate, and 3 moles of the current substance, oxygen. The mole ratio is 2 to 3, potassium chlorate to oxygen. The mole ratio is the central part of the stoichiometry solution, and we place it at the center of the solution equation. Step 4 is to get into moles. More specifically, it is to get into moles of the known substance, oxygen. The 11 liters of gas has to be converted into moles of oxygen. But how? Returning to the graphical guide developed earlier in the lecture, is there a conversion factor that converts liters of a gas into moles of a gas at STP? Yes, there is. It is the molar volume at STP. Insert the molar volume with the 22.4 liters of oxygen in the denominator so that the liters of oxygen cancel out. Further observation of the solution equation shows there to be moles of oxygen in the numerator of one fraction and in the denominator of another. Moles of oxygen cancel out. Step 5 is getting out of moles of potassium chloride into grams of potassium chloride, as asked for in the problem. What conversion factor turns moles of a substance into grams of that substance? It is the formula weight of the substance, and given here is 123 grams of potassium chloride in 1 mole of potassium chloride. The formula weight is oriented so that moles of potassium chloride cancel out, leaving grams of potassium chloride as the remaining unit. Taking out our calculator and multiplying the values of the numerator together, and then dividing by the values in the denominator, has us come to an answer of 40.3 grams of potassium chloride. 40.3 grams of potassium chloride can at most decompose into 11 liters of oxygen at STP. Since some students prefer to solve the parts of the stoichiometry solution individually, those calculations will also be shown. Getting into moles of the current substance has 11 liters of oxygen multiplied by the molar volume of oxygen at STP. Units of liters cancel out, and an equivalent of 0.491 moles of oxygen is obtained. Put that value before the mole ratio. And canceling moles of oxygen leaves 0.3274 moles of potassium chloride. This is not the time to concern ourselves with significant figures. That comes after all the calculations. Units of the desired substance are in moles. To get them out of moles and into grams, multiply by the formula weight of potassium chlorate. Moles of potassium chlorate cancel, leaving the same answer we got using the single solution equation. Stoichiometry is inherently complex because it contains multiple conversions. Keeping track of the units helps keep the process orderly. On to a second molar volume problem. A lab experiment has hydrogen gas being captured from a reaction of aluminum with sulfuric acid, aqueous. At STP, what volume of H2 is produced when 4.25 grams of aluminum is completely consumed in the reaction? This is the mass to volume type of stoichiometry problem. The first step, of course, is to balance the chemical equation. The absence of coefficients is an indication that the reaction is not balanced. Coefficients are added, and a tally is made to verify that there is an equivalent amount of atoms on the reactant side as is on the product side. Note that the sulfate ion is included as a whole in the tally, since it is unchanged in the reaction. This topic was discussed in the Balancing Chemical Equations lecture. On to step 2. What is known and what is not known in this problem? The problem gives a specific amount of aluminum. That is a known quantity. The volume of hydrogen gas is not known and is in fact asked for in the problem. It is an unknown. It is our desired substance. Since we are dealing with gases, information about the other properties of a gas are also important. In this problem, temperature and pressure are given in the form of STP. It should be added to the setup. If it's needed, we can break STP down into specific temperature and pressure, but it will not be needed here. Step 3 is to find the mole ratio from the balanced chemical equation. The desired substance in this problem is the hydrogen gas. The balanced chemical equation says that there are 3 moles of this gas. The current or known substance is the aluminum. There are 2 moles of that substance. The mole ratio is therefore 3 to 2, hydrogen to aluminum. The first 3 steps are complete, and the mole ratio is inserted into the center of the solution equation. Step 4 is to get the given substance into moles. Specifically, it is to get moles of aluminum from grams of aluminum. What conversion factor facilitates this transition? It is the atomic mass of aluminum, which is 26.98 grams of aluminum per mole of aluminum. The orientation of the atomic mass is such that grams of aluminum cancel out. Canceling out moles of aluminum leaves moles of the desired substance, hydrogen gas. The final step is to get out of moles of gas into the asked for units of volume. What conversion factor takes moles of a gas and converts it into liters of that gas at STP? It is the molar volume at STP. 1 mole of gas occupying 22.4 liters of volume. The molar volume is oriented with moles of hydrogen in the denominator, so that they cancel out with moles of hydrogen in the mole ratio. With hydrogen in units of liters, it is time to multiply and divide the numbers in the solution equation, omitting multiplying and dividing by ones. 4.25 times 3 times 22.4 divided by 26.98 divided by 2 is a value of 5.29 liters of hydrogen gas. 4.25 grams of aluminum can at most produce 5.29 liters of hydrogen gas in this reaction. Solving the problem in individual calculations begins with the calculation to get into moles. The starting value of 4.25 grams of aluminum is multiplied by the atomic mass of aluminum. Canceling out grams of aluminum produces the equivalent amount of 0.1575 moles of aluminum. Inserting that value before the mole ratio and canceling out moles of aluminum produces 0.2362 moles of hydrogen gas. That is how many moles of hydrogen that can be produced from 4.25 grams of aluminum in this reaction. Take that mole value and get out of moles of hydrogen into liters of hydrogen with the molar volume, which, at STP, has 1 mole of gas occupying 22.4 liters of volume. Canceling moles of hydrogen and doing the math gives that same 5.29 liters of hydrogen. And now to a couple stoichiometry problems that employ the ideal gas law equation. This one says to consider the combustion of gasoline octane in air, O2. How many liters of oxygen would be needed to produce 25.0 liters of carbon dioxide? To keep the problem on the less complicated side, both gases are at 125 degrees Celsius and 4.55 atmospheres. Information about one substance will be turned into information about another substance. Stoichiometry. This is an example of the 4th type of stoichiometry problem, volumes of gases. It takes a fair amount of work to get this equation to balance. The tally shows that the same number and type of atoms are in the reactants as are in the products. Yeah, a fair amount of work. Step 2 in the process is a bit easier, finding the known and unknowns. The problem tells us 25.0 liters of carbon dioxide is produced. Add that to the setup as a known quantity. Liters are the given unit and CO2 is the given or current substance. It also asks how many liters of oxygen are needed. Oxygen is the unknown. It is the desired substance with wanted units of liters. Is that it for knowns and unknowns? When dealing with gases, additional gas properties are usually required. Importantly, temperature and pressure are also given. These gas properties will be needed when the ideal gas law is employed. From our study of gases, we should recall that calculations involving temperature have to be in Kelvin scale. A quick conversion is needed. The conversion equation has the temperature in Kelvin being equal to the temperature in Celsius plus 273. 125 plus 273 is 398. 125 degrees Celsius is 398 Kelvin. Replace temperature values in the setup, and we're ready to move on to step 3, the mole ratio. The desired substance is oxygen, and the balanced chemical equation says it is at 25 moles. The current substance is carbon dioxide, and it is at 16 moles. Remember, values from the problem never find their way into the mole ratio. The mole ratio for this problem is 25 moles of oxygen over 18 moles of carbon dioxide. This conversion factor anchors the stoichiometry solution equation. Step 4 is getting into moles of the given substance, carbon dioxide, from the 25.0 liters of carbon dioxide. How is that transition accomplished? Returning to our graphical guide, we see that getting into moles from gas properties is through a modification of the ideal gas law equation. To use the ideal gas law, 3 of the 4 gas properties have to be known. The getting into moles part of this solution will use the modified gas law equation. If we multiply P times V and divide by R and T, we will have a mole value that can be placed in front of the mole ratio, just like every other stoichiometry problem. Volume is given, as is pressure and temperature. To solve for N, take that given volume amount and multiply it by the given pressure of 4.55 atmospheres. Divide by the appropriate gas constant R and the temperature in Kelvin. Liters cancel, atmospheres cancel, and Kelvin cancels. If we were to do the math on this part of the solution, we would get 3.48 moles of carbon dioxide. Moles of carbon dioxide also cancel. Now, we did not need to do the getting into moles calculation here. It was done to demonstrate the get into moles part using the ideal gas law. But we will leave it like this to help reduce the clutter. At this point in the solution, the moles of oxygen are calculated to be 4.835. Unfortunately, the problem is not solved by just finding moles of oxygen. The problem wants the amount of oxygen in units of liters. What converts between moles of a substance and its volume in a gas? According to the graphical guide, getting out of moles and into volume uses the ideal gas law solved for volume. That is the equation we need to move from moles of the desired substance to ask for units of the desired substance. On the left-hand side of the equation, there is the variable N, which stands for moles. Steps 1 through 4 provide the mole value for oxygen. These steps are the N in the modified ideal gas law equation. To get volume, that N needs to be multiplied by R and T, and then divided by P. The R is the gas constant with appropriate units. T is 398 Kelvin. And pressure is 4.55 atmospheres. Moles of oxygen cancel out, as do ATM and K, leaving just units of volume. Yes, unit canceling is a busy affair in the problem, and so is the math. Appropriate use of the calculator will give a volume of 34.7 liters. Indeed, a very busy equation. What allows so many pieces to come together in a final solution is focusing on one conversion at a time and using the units to keep the correct orientation of the conversion factor. A second pass-through using individual calculations can help reaffirm the process. Reducing the clutter a little bit, this problem can be solved in parts starting with a getting into moles. The given volume amount of 25.0 liters of CO2 is converted into moles of CO2 using a modification of the ideal gas law. Inserting pressure, the gas constant R, and temperature, and canceling units gives an equivalent value of 3.481 moles of carbon dioxide. Insert that value before the mole ratio. Canceling moles of carbon dioxide leaves 4.835 moles of oxygen. That value is converted into liters of oxygen using the ideal gas law with volume isolated on one side of the equation. Multiplying the N of 4.835 moles by the gas constant and the temperature, and then dividing by pressure, cancel units, and 34.7 liters of oxygen can produce as much as 25.0 liters of carbon dioxide in this combustion reaction. The stoichiometry problem with gases are essentially solved the same way as other stoichiometry problems. Get into moles, mole ratio, get out of moles. The second example problem says that acids can be neutralized by the addition of base. 0.100 liters of a 3.00 molar sulfuric acid solution is neutralized by the addition of baking soda, NaHCl3. What is the volume of the gas released? A temperature and pressure of 25 degrees Celsius and 1.0 atmospheres are provided. This is a stoichiometry problem because we are given amount information about one substance and asked for amount information about a different substance. This is the fourth type of stoichiometry problem. It has both solution volume with the concentration and gas volume. It's about as complicated as these problems get, but it solves in the exact same manner. Starting with the chemical equation, it needs to be balanced. Inserting the appropriate coefficients and making a tally shows that the reactants and products have the same number and type of particles. Again, the sulfate is included as a whole in the tally since it is unchanged in the reaction. Step 2 has us scour the problem for knowns and unknowns. Given a volume and concentration for the sulfuric acid, the amount of sulfuric acid is dependent on both of these quantities. Add them to the setup. And the unknown substance in the problem? It is the volume of gas produced in the reaction. The only gas product is carbon dioxide. So the volume of gas will be dependent on the amount of carbon dioxide. The unknown, therefore, is liters of carbon dioxide. The wanted units are liters, and the desired substance is CO2. Is that it for knowns and unknowns? When dealing with gases, additional gas properties are usually required. The problem says that the products will be at 25 degrees Celsius and have a pressure of 1.0 atmospheres. Those values need to be included in the setup of knowns and unknowns. As with the last problem, we will need to convert the temperature into the Kelvin scale. Temperature in Kelvin is equal to the temperature in Celsius plus 273. Inserting the 25 degrees Celsius and summing the values has 25 degrees C being equal to 298 K. Switch out the 25 degrees C for 298 K. This problem has a lot of moving parts. The gathering of information and the development of the setup is where the greatest amount of thinking and the greatest care needs to be done. It is not where the problem is solved. It is where the problem is understood. Moving on to step 3, finding the mole ratio. The mole ratio has moles of the desired substance over moles of the current substance, with moles coming from the balanced chemical equation. The desired substance is carbon dioxide, and there are 2 moles of those. The current substance is the sulfuric acid, and in this equation, it has an implied coefficient of 1. The mole ratio is 2 moles of carbon dioxide over 1 mole of sulfuric acid. Place the mole ratio in the center of the solution equation and move on to step 4, getting into moles of the current substance, sulfuric acid, from a volume of aqueous sulfuric acid. Is there a conversion factor that moves from the volume of an aqueous solution into moles of that substance? In the stoichiometry problem-solving lecture, we developed a graphical guide that showed the conversion of getting into and out of moles when weight and volume were used. It says to use molarity of the substance and have it oriented with liters in the denominator. We are given a molarity for the sulfuric acid of 3.00 moles of sulfuric acid per liter. Cancel out the liters, as well as the moles of sulfuric acid. At this point, we have converted from a volume and concentration of sulfuric acid to moles of carbon dioxide. Step 5 takes those moles and converts them into the asked for units of volume. This is the more involved part of the problem, so we will slow it down a bit and increase our focus on this important conversion. After step 4, the solution equation should give moles of the unknown substance, and it does. In this reaction, 0.100 liters of 3.00 molar sulfuric acid can produce as much as 0.60 moles of carbon dioxide. In the graphical representation developed in this lecture, we saw that getting out of moles into volume uses the ideal gas law equation solved for volume. That is the equation needed to move out of moles of the desired substance and into asked for units of volume of the desired substance. On the left-hand side of the equation, we see the variable for moles, n. That is what is calculated in steps 1 through 4. Spreading the equation out some, a volume can be found when the moles of CO2 gotten from steps 1 through 4 is multiplied by R and T and then divided by P. The R is the gas constant. From the setup, T is 298 K. And pressure is 1.0 atmospheres. This mathematical expression is N times R times T over P equals V. Canceling units is a bit more complex, starting with moles of carbon dioxide, and then atmospheres of pressure, and Kelvin. The only unit left over is liters. Clearly the math poses a challenge. One way to minimize calculator mistakes with an equation this long is to do the entire problem twice. If the final volume doesn't come out the same, then repeat the calculation until you come up with a common value. It should be 0.50 liters of CO2. In this reaction, 0.100 liters of a 3 molar sulfuric acid can at most produce 0.5 liters of CO2. Cleaning up the equation and looking at the solution in 3 parts has the 0.100 liters of sulfuric acid being multiplied by its molarity of 3.00 to get into moles. Canceling liters has 0.100 liters of the 3 molar sulfuric acid containing 0.300 moles of sulfuric acid. Get into moles. Place that value in front of the mole ratio, oriented to cancel moles of sulfuric acid. Leave 0.600 moles of the wanted substance, carbon dioxide. That mole amount is the N in the ideal gas law equation solved for volume. To get volume, multiply it by R and T and divide by pressure. Cancel units, and the math is the same, 0.50 liters of carbon dioxide. The individual conversions in a stoichiometry problem involving the ideal gas law are developed in earlier lectures. Combining them into a single solution is still difficult and needs practice. As a recap, stoichiometry is the calculation of relative quantities of reactants and products in chemical reactions. The first topic of the lecture was limited reactants or reagents. In a chemical reaction of 2 or more reactants, one reactant is almost always used up before the other or others. That reactant is called the limiting reactant. The other reactants are called the excess reactants. The process to determine which of the reactants is the limited reactant starts by solving the stoichiometry equation for each reactant using a single product. To get the limited reactant, choose the reactant that produces the smallest amount of product. The other major topic of the lecture was gas stoichiometry. At standard temperature and pressure, 1 mole of gas occupies a volume of 22.4 liters. The ratio of moles of a gas to its volume is referred to as a molar volume. The 4 properties of an ideal gas are related as PV equals nRT. That is referred to as the ideal gas law. Stoichiometry problems are solved in 3 parts. Commonly, they are summed up in the refrain, get into moles, mole ratio, get out of moles. The central part is the mole ratio and is only affected by the balanced chemical equation. When dealing with gases, stoichiometry problems usually have the amount of gas presented as a volume. We looked at 2 ways that gas volume can be converted into moles. One uses the ideal gas law equation with moles isolated on one side of the equation. The second setting was a gas at STP and used a molar volume ratio of 1 mole to 22.4 liters of gas. Getting out of moles and into volume used the same 2 relationships but oriented in a different manner. The ideal gas law has volume isolated on one side of the equation, and molar volume at STP is flipped so that moles are in the denominator. And that concludes our lecture. Gas stoichiometry is still a 3-part problem.